Welcome to another episode at Hacking Science. Today, we're cutting straight to what you could call the origin story of modern deep learning. We're diving into a paper that really changed how we build and train these complex AI systems.
We are. This is a deep dive into the 1998 landmark paper, Gradient-Based Learning Applied to Document Recognition, authored by the foundational team of Yann LeCun, Leon Botou, Yoshua Bengio, and Patrick Hafner.
Okay, let's unpack that. I mean, a lot of people know this paper because it introduced LeNet-5, one of the earliest, practical convolutional neural networks, CNN.
Right, but the architecture, the LeNet-5 part, is only half the story.
Exactly. The real mission of this work, and what makes it so groundbreaking, was pioneering this idea of taking a huge multi-step real-world task.
Something like reading every single handwritten number on a bank check.
Right. And training that entire pipeline from start to finish as a single unified entity.
That's the critical distinction. I mean, before this, you built systems out of these individually optimized modules. You'd have one tool for finding the number, another for isolating the characters, a third for recognizing them.
And they wouldn't really talk to each other properly.
Not in a learning sense, no.
Mm.
This team showed how to apply gradient-based learning globally to the whole thing. And that created a system that was just far more accurate and robust than anything that came before. That's our mission today,
Yeah.
to understand how that combination of architecture and a new training philosophy built the foundation for so much of modern AI.
So let's start with the backstory. The LeNet series, it wasn't an overnight revelation, was it?
Oh, not at all. This was a decade-long research effort spanning from about 1988 to 1998, mostly at AT&T Bell Laboratories.
And that timeline, it really shows this crucial shift in thinking, right? Away from manual engineering.
Absolutely. The very first network they published back in '88 for handwritten zip codes was still kind of a hybrid approach. It needed a lot of manual work, a lot of specialized knowledge just to get it working.
I remember reading that for that early '88 version, the convolutional kernels, the little filters that are supposed to detect things like edges or corners, they were literally hand-designed.
They were. It was an engineer telling the network, okay, this is what an edge looks like, so use this filter. This, reliance on human intuition, it really limited how far it could go.
So what was the breakthrough?
The real breakthrough came a year later, in 1989, with the prototype they called LeNet-1. This is the first time they successfully applied the backpropagation algorithm to train all the parameters in a practical, real-world task, like recognizing handwritten zip codes from the USPS.
So that was the turning point, the moment they realized, hey, we can rely more on automatic learning and less on hand-designed heuristics.
Exactly, and they built this core philosophy around it. Success comes from minimizing the number of free parameters in the network.
Which is almost counterintuitive, isn't it? You'd think more complexity, more parameters would mean better performance.
Right, but they argued against that. By constraining the network, with things like weight sharing, they showed you dramatically improve its ability to generalize. The network was forced to learn robust, general features rather than just memorizing noise in the training data.
And the results came pretty quickly.
They did. By 1990, the network was working on USPS data and getting an error rate of only 1% with a 9% rejection rate, which was really strong for the time. It proved this whole idea was feasible.
And that success led to the development of the MS database, right?
It did. In 1994, they formalized MNest, which I'm sure, became the benchmark for handwritten digits. And that data set was the foundation for training all the later versions of LeNet-4 and ultimately LeNet-5 in the 1998 paper.
Okay, so let's turn to LeNet-5 itself, the 1998 version, 7 layers, not counting the input, and it's credited with setting the blueprint for modern CNNs.
It really is. It's the model that defined the fundamental motifs we still use today. You have your convolutional layers, the C layers for finding spatial features. Then you have subsampling layers, the S layers. In LeNet-5, they used average pooling to shrink the dimensions. And then, at the end, fully connected layers for the actual classification.
And the activation function was a big deal, too.
Right. They used the hyperbolic tangent, or TAN. It gave them a really robust nonlinearity.
One detail that always strikes me is the input handling. They took a 32 by 32 pixel image, but the biggest character was only 20 by 20. Why pad it so much? It seems a bit arbitrary.
It wasn't arbitrary at all. It was actually a really clever way to build in robustness. By making sure the character has all this space around it, they guaranteed that its most critical features, like a sharp corner or a loop, would consistently fall into the center of the receptive field for the higher level feature detectors.
Ah, so you're stopping a key feature from falling right on the edge of a filter, which might confuse the network.
Exactly. It just simplifies the learning task.
Mm.
And on top of that, they normalized the input pixel values, making sure the background was 0 and the foreground was 1. This small pre-processing step actually speeds up learning quite a bit because it helps stabilize the gradients during backpropagation.
Okay, now let's dive into something I think was a huge innovation for 1998. The C3 convolutional layer. It used partial connectivity. Why do that? Why not just connect everything to everything?
Well, part of it was computational. You have to remember the hardware they were working with.
Sure.
But the deeper reason was to break symmetry and force the network to specialize. See, if every feature map in that C3 layer saw the exact same inputs from the layer before it, S2, they would all tend to learn very similar redundant features.
They'd all just become slightly different edge detectors.
Precisely. So by forcing different C3 maps to look at different subsets of the inputs, you're essentially creating specialized teams inside the network. One feature map might learn to spot the curve of a 3-fic, while another focuses on the vertical line of a 1 or a 7. That specialization was key.
And this all leads up to the output layer, which didn't use softmax like we do today. They used something called Euclidean radial basis function units, or RBFs.
Right, and the RBF units were designed specifically to produce a measure of penalty, not a probability. The output is basically the distance between the network's final feature vector and an ideal template vector for that class.
So the further away your features are from the ideal 7, the higher the penalty.
Exactly. It's measuring the lack of fit. And that concept of a penalty is what brings us to the secret sauce of the paper, applying gradient-based learning to the whole system.
The graph transformer network.
The Graph Transformer Network, or GTM. That's the real breakthrough. I mean, think about a real document recognition system. You have field extraction, segmentation, recognition, post-processing.
And traditionally, you'd train each of those separately.
Right, which is suboptimal. The system is only as good as its weakest link. An error in segmentation could doom a perfect recognition module downstream. The GTN paradigm let them train the entire multi-module system globally, minimizing one single performance measure for the final document error, not just the character error.
But how did GTNs handle something like a bank check, where you have variable numbers of digits? A normal neural network needs fixed size inputs and outputs.
This is where GTNs are so powerful. The state information isn't represented by a fixed vector, it's represented by a directed graph. As the system reads a number, it explores all these different potential interpretations, and the graph structure lets them track all possible paths, with each path carrying those numerical penalty scores from the RBF units.
So it's like the system is considering thousands of interpretations at the same time, each with a running penalty score.
That's the idea. And this brings us to the biggest headache in document recognition: segmentation. How do you reliably split up handwritten characters?
It's famously difficult.
It is. So to get around that, they introduced the Space Displacement Neural Network, or SDNN. And SDNN is basically the LeNet-5 architecture replicated and scanned continuously across the whole input field. It gets rid of the need for segmentation heuristics by just implicitly looking at all possible segmentations.
Wait, that sounds revolutionary, but if you're replicating the whole network and checking all possible splits across, say, a 9-digit number, wouldn't that be incredibly slow, especially on 1998 hardware?
That's where the magic of the CNN architecture comes in. Because of weight sharing, when the SDNN scans over by 1 pixel, you don't have to recompute everything. You only compute a thin slice of new states for the incoming pixels. Most of the computation from the previous step is just reused. That efficiency is what made it feasible in real time.
So the weight sharing that's so good for feature detection also makes segmentation efficient. That's really elegant.
It is.
So when they were training this whole global system, what was the optimization criterion? You mentioned discriminative forward training. How did that solve the collapse problem?
Ah, right, the collapse problem. So this happens when the network finds a lazy way to minimize the error. For instance, it might just set all its outputs to a constant low value. It's technically a low-error solution, but it's completely useless because it's ignoring the input.
It's cheating the system.
It's totally cheating. Discriminative forward training prevents this. It's a soft approach that focuses on maximizing the probability of the correct interpretation. It avoids that trivial zero-output solution, and crucially, it concentrates the training effort only on the examples where the system actually made a mistake.
So it's a really efficient way to solve the classic credit assignment problem. When the final answer is wrong, where do you place the blame?
It's the ultimate solution for that in a system this complex. When the final check amount is wrong, discriminative forward training efficiently sends that correction signal all the way back through the entire graph, pinpointing where the error really came from.
And this technical success translated directly into real-world results. On MNIST, LeNet-5 got a raw error rate of 0.95%.
Which was significantly better than its rivals at the time. I mean, support vector machines were at 1.1%, and older neural nets were up around 3.8%. But what really mattered for commercial success was its efficiency. LeNet-5 only needed about 260,000 multiply adds for one classification.
Efficiency is viability. A system can be accurate, but if it needs a supercomputer, it's not going into a product.
Exactly. LeNet-5 was lean enough to be deployed onto AT&T DSPs, these digital signal processors. It was integrated into NCR check reading systems and ended up reading millions of checks per month. It was one of the very first systems to prove that neural networks weren't just a theory, they were practical industrial tools.
And its legacy is just undeniable. LeNet-5 defined the basic blocks of CNN's convolution, pooling, weight sharing. When CNNs finally had their huge moment in 2012 with AlexNet, they were standing directly on the shoulders of LeNet.
Looking back, the achievement of this paper wasn't just designing a good feature extractor. It was creating this fully unified system that learned feature extraction, context, and segmentation all at the same time, all driven by a single gradient.
Right. The core message was to stop relying on hand-designed heuristics and move toward automatic global learning across these big multi-part systems.
And that idea is, it's still so relevant. Today, we're building these massive AI systems that deal with structured, dynamic data language models, interacting with code, generative models, working in 3D space.
And we're still struggling to train them seamlessly and globally.
We are. The principles they pioneered with graph transformer networks, using graphs to manage complexity and pushing gradients through non-vector data, they still hold immense potential for unifying learning in modern AI.
So the challenge remains the same, really.
It does. Nearly 3 decades later, the question is still the one this paper addressed. How much more can we truly unify the learning process across these complex hierarchical systems? Their work provides the roadmap for solving AI's next generation of integration problems.
A fascinating question to think about. We hope this deep dive into the foundations of CNNs and GTNs helps you understand why 1998 was such a pivotal year in the history of deep learning. Now go forth and continue exploring these incredible ideas.